Welcome back. So today we're going to look at phasors and also why it is so important to learn them, and also solve a bunch of problems that you might expect in the fundamentals of engineering exam. So if you have a multiple amount of sinusoidal waveforms all having same frequency, they're going to superimpose on each other, and you're going to have one signal that is going to be somewhat like that. That is the equivalent signal. So because all of these signals are time varying, which means the value changes with respect to different what time you are in, that is the horizontal axis, finding this becomes very difficult. So this can be if you're measuring a bunch of current waveforms, you need to find the equivalent current. How are you going to find it? What's the total current? If you're measuring a bunch of voltage waveforms, how are you going to measure the equivalent voltage? So that is where phasors come into play. So we use something called analytical representation, where for a signal having same time period, we consider the voltage or current, which is generally the magnitude, or it's the other way around. We consider the magnitude of the signal, which is generally the voltage of the current, or the current, and we also consider phase, which is the phi term. So we take only these two factors, and for the time being we ignore the time period, and we represent phasors as just a line at a certain angle. So this is going to be magnitude, and this is going to be the phase of the waveform. So if you have multiple waveforms, you have V1, V2, and up to Vn. So you have multiple phasors. So now what's the benefit of it? Like earlier we saw, we had multiple waveforms. It was very difficult to get the equivalent or the end result of when the waveforms superimpose on each other. Now the calculation becomes very simple because we are not considering time. So the magnitude is the same, and usually this magnitude is the RMS value. So if you have a voltage phasor, it's usually the RMS voltage, and if you have the current phasor, this magnitude is the current RMS current value. Alright, so now if you have these, you can do very simple vector operations and end up with your equivalent phasor. So this can be the total result of the superimposed current or superimposed voltages. Alright, so let me show you what phasor representation looks like. So your phasor is going to be rotating in a circle. So you have your sinusoidal waveform going in a certain pattern. Your phasor is going to rotate like this. So it's going to be here, it's going to move here, and it's going to move here. So it's going to rotate within a circle. Your sinusoidal waveform used to rotate I used to have a certain pattern as well. So this is kind of like the rotation of the wheel of your car. And even though your wheel of the car rotates in a circular motion, your car moves forward, linear. So if you plot this at different points in time, you would get a sinusoidal waveform. So a phasor representation can always be mapped to find the instantaneous value at a certain time. So it's not that complicated, or we're not changing anything that much. So phasors have three ways. You can represent a phasor, a voltage phasor, or a current phasor in three ways. One is just having magnitude at an angle. So I can say like 10 at an angle 30 degrees. So this is 10 volts at an angle 30 degrees. So that is the polar form of representation of a phasor. Another phasor form of representation is the rectangular form, where you can have 10 plus J20. So usually this comes when we deal with inductors and capacitors. So we will see when we solve the problems, this J20 is generally caused by an inductor of inductance 20 Henry. I mean, it's not going to be 20 Henry, but it is. And there's lastly the differential form, which is represented as something like 10 e to the power of j theta. We're not going to deal with the differential form much, but the polar form and the rectangular form are the two most commonly used ones. And to convert convert between them, there is a separate video that I've made where you can convert from polar to rectangular using your calculator. So you feel free to check out that video, guys. All right, without further ado, we have our phasors. We use the phasors because we want to know what is, if we superimpose, what is the net result that we get. And so that is the main reason. We cannot do this if you have a bunch of waves. You cannot do that because they're time varying, so they're not having a fixed value. But when you take out the time dimension of it out of the picture and you just represent it with the magnitude and the phase, now you can do very simple operations to find the equivalent voltage or current. All right. Okay, so we come to our first problem now. Now this is where you start to apply your phasor knowledge. So this is a sample problem that you can encounter in the FE exam. So you have a voltage, time varying voltage source, and let me write that. This voltage source is given by 100 sine 377 t plus 60. Alright guys, so we have this voltage source and we're being asked to find the current, the phasor current. Alright, so this circuit has just one inductor of 100 millihenry. So this is going to have a lot of steps. So the first step is we are always representing the voltage phasor as a cosine wave. So it can be max or be RMS cosine omega t plus phi. But since it is in the sine, it's in the sine form, it is not an issue at all, because remember, sine and cosine are just interchangeable waveforms by 90 degrees phase. So we're going to do the first thing, it is convert this to a cosine wave. So I'm going to write it down here. It's just going to be 100 cosine of 377 t plus 60 minus 90 degrees. Because I'm going to write it down here, your cosine wave is nothing but, your sine wave is nothing but your cosine phase shifted by 90 degrees. So that is what I'm using here to convert that. So I would get my V value as 100 cosine 377 t minus 60 degrees minus 90 degrees is negative 30 degrees. Alright, so this is our expression in our standard form. So now we can obtain our phasor by taking this magnitude and this phase. So I'm going to take this magnitude, but it's the peak value and I want the RMS value. So to get the RMS value, I'm just going to divide 100 by root 2, or I'm going to write V, so it's going to be Vm divided by root 2, and that's going to be 70.7 volts. So my voltage phasor is nothing but, it's just uppercase V is 70.7 at an angle of negative 30 degrees. So in my phasor diagram, I would just represent it as having a magnitude. Okay, this is definitely not 30 degrees, but something like this. So it's got a magnitude of 70.7 at an angle of 30 degrees. So that is my voltage phasor. Okay, so the next part is we need our impedance. So remember, this problem had 100 millihenry inductor in series, and to get impedance of an inductor is omega times L. So if you had watched my inductors video, you would have, we actually did this, where impedance of an inductor is omega times L. Now what is omega? So here omega is the coefficient of T, so that's 377. So our impedance is 377 times 100 millihenry 10 power minus 3, and that is 37.7. Now what is the angle going to be here? So in an inductor, your voltage phasor is always going to lead So this is my voltage phasor and this is my current phasor. It's always going to lead by 90 degrees. In a capacitor, it's going to be the opposite. So this is going to be the current phasor and this is going to be the voltage phasor, and it's going to be, the current is going to be leading. So because it is an inductor, remember this is ideal case, and because here we are saying the inductor has no resistance, it has pure inductance. So here, because of this reason, we are going to give our angle as 90 degrees. So if we were dealing with a capacitor, it would have been negative 90. But since it is an inductor, it is a positive 90. So now I have my voltage and my impedance. So my current phasor is just going to be voltage phasor by impedance phasor. So my voltage phasor was 70.7 at an angle of negative 30 degrees. And my current phasor, impedance phasor was, let's see what it was, 37.7 at an angle of 90 degrees. Now phasor math, how are we going to solve this? It's very simple. We are going to do this operation as it is. So 70.7 by 37.7 would give me 1.8. And we're going to do this operation as a simple difference. So minus 30, negative 30, and negative 90. So that's going to be at an angle of negative 30, negative 90 is negative 120 degrees ampere. So this is our final answer. So let me plot this. So if we plot this, how is it going to look like? So we had our voltage phasor, which was at 30 degrees, sorry. We had our voltage phasor 70.7 volts at 30 degrees. And now we found our current phasor is 1.8 at negative 120. So this is negative 90, so negative 120 is somewhere here. So our current phasor is 1.8 at an angle of negative 120. Well, I don't need to write the negative sign here because I'm going in the other direction. Okay, so this is your voltage phasor, or just uppercase V, and this is your current phasor. So now you don't have to deal with time varying signals, you can just deal with straight lines and do very simple math such as this to use the Ohm's law. Alright, so always remember guys, you got to remember this part though. If you're dealing with inductors and you're finding impedance, in ideal inductor, the voltage always leads by 90 degrees. In a capacitor, the current leads. So it's just the opposite of it. Alright? Okay guys, so we're going to solve our second problem. Sorry about my handwriting, it's not that great. So this is supposed to be 100, but it looks like something else. Okay, let me write it down here. Okay, so our next problem says we have a voltage signal, time varying voltage signal of 100 cosine 377t, and there's no phase shift. Now you might ask, why are we getting this 377t? Well, if you consider this as 2 pi f and you take f is 377 divided by 2 pi, the value you would get is 60 hertz. So in the United States, the electric power is always, if it's a sinusoidal, it's always kept at 60 hertz. So that is why this 377t comes. But I just wanted to show you why in every problem that we have, we're getting 377t. It's because your frequency is at 60 hertz. Alright? Okay, I'm gonna clear that out. So this is our voltage, and as usual we're gonna get our voltage vector first. So I would need my voltage RMS, that would be Vm by root 2. So that is once again 100 by root 2, which is 70.7 volts. And what what is the angle here? Well, since we have 0 phase shift, it's going to be 0 degrees. Alright, now let us find the impedance. So we have 500 and we have the impedance of the capacitor negative J100. Remember, if you ever see capacitor impedance as positive, that's just not wrong, because capacitor impedance is always negative. Now let's go and find the Z phasor, which is going to be 500 minus J, and what this was J100. Alright, so this is in the rectangular form and I want it in the polar form. So to convert to polar form, and I would get my magnitude as square root of 500 square plus 100 square, and my angle would be inverse tan of negative 100 by 500. So if I consider do all these calculations, but I also, once again, just like in the last problem, you can check it out. I've made a video on how to do it in a calculator. If you have a scientific calculator, you can just put those values in, press. It's simple as pressing a button. You shift from polar to rectangular form. So this value would be just 500, and this angle right here would be at an angle of negative 11.3 degrees. So I have my voltage phasor, I have my impedance phasor. Now my current phasor is just going to be V by Z. So that's 70.7, sorry, it's not degrees, at an angle of 0 degrees divided by 500 at an angle of negative 11.3 degrees. So once again, I'm just going to divide the magnitudes, and that would give me 0.14, and my angle is going to be 0 minus of minus 11.3, so that would be just 11.3. Right, so I can just erase this and write it as 11.3 degrees. So let's plot this out, shall we? So we had our voltage phasor. So I'm going to use red for my voltage phasor. So my voltage phasor was 70.7 at an angle of 0 degrees. And what did I get my current phasor as? 0.1 at an... So I'm going to use green. Okay, it's not that long, but I'm just doing it to show you. So this is my current phasor, and it is at an angle of 11.3 degrees. So remember, because it is a capacitor, your current should always lead your voltage. So we saw in an inductor, in our last problem, the voltage was leading the current. So if you go in the anti-clockwise direction, so which is this direction, you would encounter your current first and then the voltage, because it was an inductor. Now, if we have capacitor in the circuit, if you go in the anti-clockwise direction again, you would find your voltage phasor first and then the current phasor, because the current leads the voltage, right? So do not worry too much about it. Once you get practice, you will know it just at the top of your head, the voltage which leads which. Okay, so now let us solve just one more example, and then we are gonna stop this. Okay guys, so this is gonna be our last example. So we have here a sinusoidal voltage supplied by 100 sine 377t plus 100 degrees phase shift. So once again, you know why it is 377 now, because it's a frequency of 60 hertz. Now the capacitor in the circuit has a pretty high capacitance of 100 millifarad. Now we're being asked to calculate what is the current flowing, the phasor current in this circuit, in this power system. So let's go ahead, because it is not in the standard form, it is not in the cosine form. So let's go ahead and convert to standard cosine form. Yep, so let's do that. So this is going to, my voltage signal is going to be 100 times, I always mess that up, 100 cosine of 377t plus 100 degrees minus 90 degrees. So when you go from sine to cosine, you subtract you subtract 90 degrees, because it's sine and the cosine wave are just related by a phase shift of 90 degrees. So my voltage waveform is going to have, in standard form, 100 cosine 377t plus 10 degrees phase shifted from the origin. We already know from our previous problems, if you have 100, your RMS is going to be 100 by root 2, that is 70.7 volts. And your angle is right here, it's 10 degrees. Okay, so that is our voltage phasor. And now let us go ahead and calculate the impedance phasor, or Z. So to know Z, we do not have any inductors in the circuit, we do not have resistors, so it's just capacitors. So it's just going to be equal to XC. But if you add inductors, so that would also include XL. So XC is nothing but 1 over J omega C. And XL is, we saw in our last problem, it was omega L. That looks like an angle, so I'm gonna, so it's J omega L. Okay, so but in this case we are not having this because there's no inductor, so we're just gonna do the calculation for a capacitor. So my phasor, impedance phasor, is going to be 1 over J, omega is 377 times 100 millifarad. So that is going to give me a value of 0.026. Now remember, because it is a capacitor, the voltage lags the current. So if you go from an anti-clockwise direction, you would find that the current is ahead of the voltage by 90 degrees. So my angle here is going to be negative 90 degrees. So my current phasor is going to be V by Z, so that's 70.7, and what the angle was 10 degrees, I assume. Let me check that. So yes, that is 70.7 at an angle of 10 degrees, and my impedance is 0.026 at an angle of negative 90 degrees. So once again, I am going to divide the magnitudes, and I'm going to get a value of 2665, and I am going to find the difference between the numerator and denominator. So that's going to be 10 minus 90 degrees. So that's going to be, my final answer is going to be 2665 amperes at an angle of 100 degrees. So we have our phasor plots, and the voltage, I'm going to represent it in red here. It was at an angle of 10 degrees, so 70.7 at an angle of 10 degrees. So this is your voltage phasor. And your current phasor, what we found out in the problem, was really high, and it was 2665 at an angle of 100 degrees. So this is 90, so 100 would be somewhere here. So it's 2665 at an angle of 100 degrees. So that is it for phasor representation. Remember, your entire phasor representation, we use phasors to find equivalent or the resultant current or voltage or current, because we cannot do this in a sinusoidal waveform because it varies with time. Your phasors do not vary with time, so you can pretty much do the calculations. Alright guys, thank you for watching.